Okay, this morning we have, I'll be speaking this to you. We have Chao Li here from NYU, and he'll be speaking on stable minimal surfaces in four manifolds.
All right, thanks the organizers for the kind invitation and for this beautiful job of putting everybody together. Okay, today I will talk about some interaction between minimal surfaces and as we can see, scalar curvature. Okay, so let's take a look at the setup. So we have an immersion m(n)-1 into a ambient space that I'm going to call xn with Riemannian metric. And I'm going to always assume that this is a two-sided immersion, meaning that you have a continuous choice of the normal vector field. And I'm going to also assume that it's a stable and minimal immersion. Okay, of course, minimal means that it's a stationary for the area functional, and stability for two-sided immersion. This is equivalent to say that on the surface M, the integral of am squared plus Ricci nu times phi squared is less than or equal to the grad phi squared. So this is true for every compactly supported, let's say, C1 function on M. Okay. Now, there are a couple of interesting rigidity results for this kind of a stable minimal immersion in particular, when M is closed. Namely, M is compact without boundary. Then in this case, as you can see, you can take the constant function y in this inequality, and in particular, by taking a constant function, the left-hand side is 0. So in particular, this tells us that the am is identically 0, namely the surface is totally geodesic, and Ricci curvature, this is the ambient Ricci curvature. Sorry. Let's say, let me emphasize the ambient Ricci curvature in a new direction vanish. Okay, so this is observation that dates back to at least James Simon, for instance. Okay, so
Under assumption.
so sorry. Yes, under Ricci non-negative. Okay, thank you. And then if let's say we were interested in scalar curvature, for instance, if we assume, for instance, scalar curvature of the metric on X is positive, let's say at least 1, then a very nice observation of Shen Yao, which has been the foundation of many modern applications of minimal surface theory, tells us that the induced metric M on M, well, let me just say M admits a PSC metric itself, right? Okay, and in particular in dimension 3, so when n is 3, this is particularly strong because any two-dimensional surface admitting a positive scalar curvature metric has to be a sphere. So this means that each connected component of M is diffeomorphic to S2, okay, and with the area bound as well. Okay, so again, this is assuming when M is closed, but when M is not assumed to be closed, but rather complete, let's say if M is complete, then the picture is sort of more difficult and more interesting in a way, because immediately you see that you can't just plug in the constant function, right, on a non-compact complete manifold. But still we have very interesting results, for instance, especially in dimension 3. So when n equals 3 and you assume you have a complete two-sided minimal immersion, then under various curvature conditions, you have interesting consequences. For instance, if you know the scalar curvature, ambient scalar curvature of X is non-negative, then Fisher Corporation proved that in the 80s, I guess. She proved that the conformal structure of the induced metric on M is either, you have two possibilities, either the R2 or it could be conformal to S1 cross R. It's a more restrictive case, and if this case happens, then let me just say that then in this case, you know that the scalar curvature along the submanifold M is identically 0, and Ricci nu is 0. Okay, and moreover, so I guess and moreover, we know that M is intrinsically flat, so GM is flat. Okay, so you have strong restrictions on the conformal structure, and if you assume Ricci, it's a stronger condition, Ricci G is non-negative, then its induced metric is even more restrictive, and in particular, it has A identically 0. So the consequence you get is the same one as if you can plug in the constant function 1. Okay, so it's totally geodesic and intrinsically flat, and Ricci nu identically 0. Okay, so this was proved by Shen Yao. I think in the quite famous paper in 82. Okay. So they have strong topological consequences using this flatness. For instance, let me just show you one example. It's I think a famous and beautiful theorem on 3 manifolds. So assume M3 is complete. So here we're using X, I guess. So you have a complete 3 manifold with strictly positive Ricci curvature. Then M is diffeomorphic to R3. Okay, and they prove this result using this rigidity theorem on complete minimal surfaces. Again, this is a theorem by Shen Yao. Same paper. Now, there are also interesting extensions of this result by even relaxing the condition from Ricci strictly positive to Ricci non-negative, and this is the so-called famous Milnor conjecture. Okay, so if you assume Ricci is strictly non-negative, so still you have X in a 3 manifold, Ricci non-negative, and then the fundamental group is finally generated. So and this was proven based on the Shen Yao result and the rigidity analysis by Gang Liu, I guess in 2013. Oh, sorry, yes, exactly. Thank you. Yeah, X is our ambient manifold. Okay. Okay, so in 3 dimensions, on the the study of complete minimal hypersurfaces, let's say stable minimal hypersurfaces has deep applications in topology. But just to make a parallel case with the compact picture, so we're closed picture. So let's say if you assume still in dimension 3, let's say if you assume scalar curvature of the ambient manifold is bounded below by some positive constant, say 1, then you can't really tell a lot of the, let's say, this kind of, well, you still have all the conclusions from the first, but then also you have something more. So in this case, at least you can show that M is compact. The stable minimal hypersurface is compact. Okay, so this is also due to Shen Yao in their 82 paper, same paper. So we should all read it, okay? And also independently, Gromov-Lawson had a proof. 1 year later. All right, so there are interesting applications in dimension 3. So I'm trying to discuss what will happen in 1 dimension above. So we will be focusing on n equals 4, and as we will see, if you want to draw similar conclusions on the, let's say, the rigidity or even splitting of along a minimal hypersurface, then 4 is kind of interesting dimension, maybe 5, but then even higher dimensions, the conditions will be quite unclear. Okay, so let's see. Let's begin with examples. So keep in mind that in dimension 3, if you assume Ricci non-negative, then you have totally geodesic, flatness, and Ricci identically 0. So the first example shows that in dimension 4, this is not the case. So let's say we can take, so this example is to give you a 4 manifold, which has sectional curvature non-negative, but you have a okay, so let's say strictly positive, let's say. Okay, so note that in this case, in dimension, if we're in the 3 manifold with strictly positive sectional curvature, then there can't be any stable minimal hypersurface, right? You can't have Ricci identically 0 over there, right? Okay, but then it does, in dimension 4, there are such examples where you have a stable minimal immersion. Okay, so this is actually quite easy to construct, this example. So what we can do is that we can just take X4 to be a R4. But now instead of taking the Euclidean metric, let's take G to be, write everything in polar coordinates. So let's take it to be some war product. Now if you take phi R to be R, you get the Euclidean one, Euclidean metric. And now we take phi R to, so rho of R. So we take rho R to be something like this. So let's see. So okay. All right. So let's see. Let's say take rho R over R to be the following picture. So it decreases. It's a decreasing function from 1 to some, some constant alpha. Well, sorry. We're really taking the derivative to be this picture. Okay, and rho is 0 at the origin, at R equal to 0. Okay, and it's a slowly decreasing function, with which limit to alpha, and such that alpha is sufficiently close to 1. Okay, now you can compute the sectional curvature of this metric, and by taking this, you can sort of see that the sectional curvature is always positive, but it's decreasing to 0, near infinity. And the upshot of, is that, it's a rotationally invariant metric, so the normal R3 is a totally geodesic embedding, right, in this R4. This is totally geodesic. So we only need to verify the stability inequality, okay? So the stability comes from the following sort of well-known Hardy inequality. So on R3, Hardy inequality says that for every function, compactly supported function, we have, let's see, you have a sort of, sum factor of 1 over 4 R squared times phi squared. So this is true for every compactly supported C1 function. Okay, so then as long as we can take alpha to be sufficiently close to 1, you can verify that the sectional curvature decays, quadratically, but you can make the decay slower than 1/4. Okay, so so this Ricci nu is going to be less than or equal to 1 over 4 R squared always. Okay, now of course it's so this implies that on this R3, that phi squared is larger than or equal to, A squared is 0, and Ricci is lower than R 1 over 4 R squared, right? So so the stability holds. Okay. So the first upshot is that in a 4 manifold with positive sectional curvature, there are let's say minimal embedding, complete minimal immersion stable. Okay.
So which step of this computation fails the dimension?
Right. So let's see. So let's see. I think maybe it's the Hardy inequality. Yeah. I think that there you still have a Hardy inequality, but you can't make sectional curvature decay or Ricci curvature decay slower than this factor. Okay. All right. Yeah, that's a good question to keep in mind. Yeah, namely, let's try to compare with the three-dimensional picture always. Okay, so, and let's see a second example. Oh, good point. It's not, but as you can see, it just differs, slightly. Yeah. So I'm cheating a little bit. So in reality, with the induced matrix, not 1 over 4 r squared, but rather 1 over 5 r squared or something. Okay, so the next example is, remember when in three manifolds, if you assume ambient scalar curvature strictly positive, then you have compactness. This is not true in higher dimensions. So what you can do is that, so let me maybe write a conclusion. So this is RG strictly positive does not imply M is compact. Okay, and this is quite easy to construct. So what you can do is simply take a, for instance, you take a non-positively curved surface, let's say x1. It's a surface non-positively curved, and in those surfaces, imagine a torus, right? Then then on a torus you just take a geodesic with irrational slope. Okay, so that's a geodesic line from R to this. Well, it's a stable geodesic, let's say, from R to xg, right? Okay, so say we take sectional curvature G to be non-positive. Okay, so again, these conditions to guarantee that this geodesic is always stable. Okay, because the stability operator is just positive, pointwise positive. Okay, now what you can do is that you simply cross this picture with sigma cross R S2 epsilon, say R cross S2 epsilon to X2 cross S2 epsilon with the direct sum of the metric, where you take an S2 epsilon to be a tiny sphere, right? So then scalar curvature adds up, right? You have a non-positive but controlled Gauss sectional curvature on or scalar curvature on this two-dimensional surface, but then you take an extremely large scalar curvature concentration on S2. So this manifold definitely, this metric definitely has, you can arrange it to have scalar curvature bigger than 1, all right? But now, okay, let me, yeah, so thanks, okay. Right, so then, is it clear now? Okay. Now, of course, this is all, this immersion is stable because the first eigenfunction, one way to see it is that the first eigenfunction would be invariant on this S2 factor, right? You have a positive function that solves the Jacobi operator. Okay, so then this is stable. But of course, this is the embedding R cross S2 epsilon is non-compact. Okay. So as we can see from these two examples, the conditions that here we assume sectional curvature strictly positive, and the condition for RG let's say strictly positive bigger than 1. Individually, they do not guarantee any interesting property.
Right, there was a question in the chat, which
yes.
is, can you construct these same examples in all higher dimensions?
Yes. Yeah, all higher dimensions, yes. Okay.
Wait, Tom, could you just explain example 2 again?
Yes. So let's see. So you take any surface, fix a metric G1 such that the Gauss curvature is non-positive. Now, the stability operator for geodesics is, remember, is the f prime, let's say gradient f squared plus Gauss curvature, right? Times f squared. So that operator is pointwise positive. Okay. So this immersion is stable as a geodesic. Okay. Now you just take the Cartesian product of both sides with the S2, the sphere of a tiny radius. Okay. Now because the scalar curvature of the direct sum of a Cartesian product just adds up. right? So this guy has strictly positive scalar curvature. Okay, yeah. Okay, so these are some preliminary examples. An interesting situation will happen. The interesting conclusion will happen, as we will see, if we put together these two assumptions. So this is a theorem with Otis Chodos, myself, and Douglas Stryker earlier this year. So if you assume, right? So if you assume you have a 4 manifold, is such that first of all, we need to assume the sectional curvature of the metric G is non-negative. Okay. And let me put a star here. This condition is that. And the second assumption is that the scalar curvature of G is uniformly bounded below by some positive constant, let's say 1. And then we also need to assume that this metric, has weakly bounded geometry. So I'm going to explain this condition a little bit later. Okay, then under all the 3 assumptions, then we do have rigidity of any stable minimal immersion. Then any stable minimal immersion, let's say complete, two-sided stable, has to be totally geodesic, and the Ricci curvature, ambient Ricci nu is 0. Okay, so this is sort of an analog of the famous Shen-Yao result in dimension 3. Okay, so let me make some remarks. So first of all, write down a corollary. First of all, weakly bounded geometry, well, whatever bounded geometry means, it should be satisfied for all closed manifolds, right? Closed Riemannian manifolds. So in particular, this means that if you have a closed, let's say X4G is closed with strictly positive sectional curvature, then automatically the 3 conditions are satisfied, right? What's that?
Back to scaling.
Okay, let me write this is okay. Up to scaling, let's change it a little bit, and then automatically the 3 conditions are satisfied. Then, but in this case, you see you can't have Ricci nu 0, right? So the conclusion is that there's no complete stable, minimal immersion. Okay, apparently this was unknown even for the round S4 before. So I should write a remark here. So the famous Shen-Simon Yao paper actually does prove something in S4. So we're in S4 and 5. So the same, it's true in S4 and S5 with the volume growth condition. Assumption on M. Okay. Well, it's a complete immersion, right? So you can talk about its intrinsic volume growth. Yeah. So it's just a Shen-Simon Yao estimates, but that also works in in suitable Riemannian manifolds, curved ambient spaces with curvature. Okay. So in their paper, if you read, their technique actually works best if you're in a positively curved but constant sectional curvature space form. So particularly the spheres. Yes. Okay. Yes. So let me write a few remarks and see what we can do with this kind of theorem. So, okay, so in the first remark, let me explain a little bit of what I mean by weakly bounded geometry. Any questions? Okay. Very good point. Yeah, that's I think that's an area that we don't quite understand. I think the only reference I have in mind is the paper by Antonio Ross, who proved that even without the zooming two-sidedness, a complete stable minimal immersion in R3 is flat. So there's no one-sided immersion. That's pretty much the only like definitive result I
So the Shen-Yao results don't have any analog for the one-sided case?
It's a good point. I don't know. Well, maybe there is, but I don't know. It's unlikely, I think. Well, actually, the paper by Ross studied one-sided immersion in some positively curved 3 manifolds. I forgot the precise statement. But yeah, there are some. Okay, so let me explain first what I mean by weakly bounded geometry. So this I mean the following thing. So there exists a uniform radius positive. You can maybe think, one easy way to visualize it is that for, we're really dealing with complete non-compact manifolds, right? So you can take R to be injectivity radius of the manifold, and we're assuming injectivity radius is uniformly positive. Well, okay, but actually we do not need that strong assumption. So so there exists the uniformly positive R such that for every P on the ambient manifold X, there exists C2 alpha local diffeomorphism phi from BR0 to the UP. So this is contained in R4, okay, and U is some neighborhood around P. So, for instance, we're only assuming local diffeomorphism, not a diffeomorphism on this whole BR, but okay, and with controlled, and let's see, phi has uniformly controlled C1 alpha. C1 alpha bounds. Okay, so for instance, one condition to guarantee this kind of the existence of such local diffeomorphism could be that the sectional curvature is two-sided bounded. So we already assume this non-negative, right? So, but let's say to guarantee the local diffeomorphisms, then this is enough, because then it's the Jacobi comparison theorem, right? The Jacobi fields are the exponential map is always a local diffeomorphism on uniform radius. Okay, and or you can also assume Ricci non-negative, or let's say Ricci bounded below, and the injectivity radius lower bound. And then this is a famous theorem by Michael Anderson. Okay, it's interesting to see, well, you remember Shen-Yao doesn't have any bounded geometry condition, right? So it's interesting to see whether we can remove this, but for our argument, we do need such a condition. Essentially, this condition, so the reason that we need it is that last year, yes. Right. Yeah, I'm just writing some sufficient conditions to guarantee this bounded geometry assumption along. Okay, so the reason is that last year, Otis and I proved that the stable Bernstein theorem in R4, so M3 embedded in R4, let's say two-sided stable, means that M is flat. So once you know a stable Bernstein theorem in Euclidean space, ideally, well, heuristically, you know curvature estimates for stable minimal immersions in any 4 manifolds, right? But that's the heuristic. So in order to make the argument work, one sort of need a weakly bounded geometry. So the idea is that essentially, if you can use these local diffeomorphisms to pull back immersion of into an ambient 4 manifold to reduce the curvature estimates in ambient 4 manifolds into this Bernstein theorem. Okay, so let me not go into that detail. So this theorem plus the weakly bounded geometry implies that curvature estimates holds in X. So the AM is less than some constant depending on x. Okay. All right. Now, again, let me not go into any details. Okay. All right. So, but I maybe this is just a technical assumption that we're not sure. Okay. So this is the first assumption, and sorry, first remark. And the second remark is that, okay, so the second remark is that the theorem fails when n is at least 6. The basic observation is that one can take the previously constructed example. So we can take the following thing. So we take R4G, where G is the previously constructed metric with slow decay near infinity, okay, positive sectional curvature. And we just cross it with some sphere. So this is the metric in the previous example. So sectional curvature is strictly positive, but decaying to 0, and we have a M3 stable M3 embedded in this R4G. Okay, but then we can simply take M3 cross S2 embeds in this X6. But you see, this manifold, first of all, it has non-negative sectional curvature, okay, because we have a product of 2 such manifolds. And then this also has strictly positive scalar curvature, right, because we're taking the Cartesian product with some S2. But now this manifold, these surfaces do not satisfy Ricci nu equal to 0, right, because, well, essentially the new direction happens in this embedding, right? The Ricci is non-zero. Okay. Okay. So heuristically, the reason is the following. But okay, this is still stable. The upshot. Again, because the first eigenfunction should be invariant in this S2 direction. So the reason heuristically that we should have such examples as we will see is that again, this is a famous observation by Shen Yao. That any stable minimal immersion inside X4G, where RG is strictly positive, should imply that M. Okay, let me just be a little bit imprecise here. So M looks like a PSA metric itself, PSA manifold. Okay. Say it again? Oh, sorry. Yes. Okay, and let me elaborate a little bit. So if you know the ambient metric has a scalar curvature positive lower bound, then M should look like a PSA manifold with the same lower bound. Okay, but in this case, there's a famous conjecture, I think, due to for instance, due to Gromov, which says that if you have a manifold that looks like a positive scale, a scalar curvature bounded from below by positive constant, then this manifold M should be microscopically codimension 2. Okay, so M is microscopically the codimension 2, so it's n-3 dimension. Okay, so this is quite, okay, this conjecture is unknown in general, but let's see what happens if we apply this kind of heuristic to our specific situation. So when n is 4, n-3 is 1. So this means M should look like a one-dimensional graph. Metrically look like a one-dimensional graph. So if you have a one-dimensional graph, then imagine okay, so you have a stability inequality on a one-dimensional manifold. Then what you do? Well, you just take the linear cutoff function, right, from 1 to 0. This gradient will converge to 0, okay, and the function converges to 1. Okay, so we can take a linear cutoff to conclude all the rigidity A 0, Ricci 0 in general, etc. Okay, and when n is 5, The conjecture heuristically means that M should look like a two-dimensional space, let's say. But in 2 dimensions, one can still do a logarithmic cutoff. Okay. To guarantee the right-hand side or the left-hand side of the stability is 0. But when n is at least 6, then M is microscopically even bigger than or equal to 3D. But on a 3-dimensional manifold, let's say on R3, okay, so you don't have any cutoff function to guarantee that it's 0 a priori. Okay, so no good cutoff. So that's one reason that this kind of example should exist. Okay.
Conjecture. I mean, I don't know what conjecture means, but does it imply that you should have volume growth that is?
Looks like that, yes.
That is to the power of.
That yes. Something sort of like that. We can't really prove the volume growth statement as you suggested, even in 4 n equals 4 case.
But that it would be a reasonable conjecture.
Right. Yeah. So a good question is what happens in dimension 5. So let me write it as a question. Yes.
The Eurison width you're talking about?
Yes. We're Eurison width. Well, okay, but if you're talking about dimension, then it's called microscopic. So if you're familiar with Eurison width, then the statement is saying M has finite n-3 dimensional Eurison width. You can find a map from M to a n-3 dimensional polyhedral space with controlled diameter of the pre-image. Maximal and Lokomovich, yes.
Is that like a confirmation of this conjecture?
In dimension 3, yes. So I guess, okay, this is known in dimension 3 for several reasons. I think,
But only for compact manifolds, good point is not.
Well, yes, but for instance, the Mill bubble technique I use with Otis can handle this kind of non-compactness. I'm not claiming we solved this conjecture for general non-compact, but specifically for this kind of heuristic, it works. Okay. All right. So this is the second remark. Again, I think an interesting question is to prove the same statement in dimension. Well, I raised a theorem, but to prove the same statement in dimension 5, namely, if you have a 5 manifold with non-negative sectional curvature and strictly positive scalar curvature, weakly bounded geometry, then you should, then any stable minimal hypersurface should be rigid. Okay, and the third remark, yes. Statement of the.
You said there's a weakly bounded geometry version of that result for stable Bernstein.
No.
Constant curvature estimate, that's all.
Yeah.
Yeah, so what was curvature? So you're saying if you have weakly bounded geometry, then the second one is bounded
by some constant dependent ambient manifold.
And the weakly bounded geometry is just a sigma alpha assumption?
Yes. So it's a C2 alpha diffeomorphism. So the pullback metrics are C1 alpha. Therefore, minimal surface equation has coefficient in C0 alpha, right? So elliptic regularity tells you graphs are C2 alpha. So you have convergence, and so the compactness argument should work. Yeah. Okay.
In relation to that, do you conjecture that to be true in dimension 5 but not higher?
Oh, well, one needs to solve the stable Bernstein first, right? The compactness and pullback argument, that's our standard. I mean.
Yeah, that's what I mean. The Bernstein.
Oh, okay. Why not? Yeah. Let's conjecture it's true in dimension 5 and 6, but and 7, let's say. Yeah.
Oh, 5, 6, and 7.
Yeah, but above 8 is false, right? So let's conjecture everything else is true. Yeah. Why not?
Oh no, I was wondering if it was related to, because you're saying that was used to prove a theorem.
Yeah.
The theorem that you won't use it to prove, you're putting a heuristic that depends on dimension.
Yeah. Right. Oh, I see. It should be okay. I don't know. I have no idea. Yeah. Okay. Let's see. So Okay, so the third remark, which is also a little bit interesting, I think, is that remember we have a sectional curvature assumption that I placed a stat here, right? So this can be replaced actually. This can be weakened. To the following condition. So sectional to the condition that any you take the Riemann tensor on let's say u v v u plus r let's say u w w u is non-negative. Okay, so remember what we're in the four dimensions, right? So this condition, well, in literature, some people call it the two intermediate Ricci curvature. Okay, so this is true for every orthonormal UVW. Okay, so again, in literature, this is called the two intermediate Ricci curvature non-negative. Okay. It's a not very well studied notion of curvature. Okay, somewhere this condition lies somewhere between the positive non-negative sectional curvature and non-negative Ricci curvature. Okay, so we can actually replace the non-negative sectional curvature by non-negative Ricci 2 curvature. So okay, so apparently since we don't know a lot about such manifolds before, maybe let me write some topological applications. Again, directly analogous to what Shenyao did in their 82 paper. So the theorem is the following. So suppose you have a X4, it's complete, non-compact, and you assume Ricci 2 is non-negative. Scalar curvature is strictly bounded below by positive constant, and weakly bounded geometry. Okay, we need every condition. Okay, so we can't prove this is diffeomorphic to R4. I'm not sure it's true or not, but we can have some topological restrictions. So first of all, H1 of X, integer coefficient, is purely torsion. We cannot prove it's the manifold is simply connected, but rather we know the first homology is torsion. Okay, there's no integral element. The second is that there's a certain, the second part is also directly analogous to Shenyao. So we use this notion of, so let's say X is H2 trivial at infinity. So basically means that you can't have a sequence of two cycles going to infinity. All of those two cycles can be written as the boundary of some compact three-dimensional domain, but those domains all intersect some finite compact set. Okay, so namely, this is equivalent to say there's no two cycles sigma j going to infinity. These are two-dimensional cycles. Sigma j can be written as the boundary of three-dimensional regions where all these regions omega j intersect some finite compact set is non-empty. A typical example where H2 is non-trivial is S2 cross R2, because then you take S2 across a very far away point if you want to fill it. Let's say at infinity it's S2 cross R2, but you patch it up at some finite set. But if you want to fill that in, you have to go back to this finite region. Okay, so this can happen. Essentially, if it's H2 non-trivial, then we can use this sequence of two cycles to construct a complete minimal hypersurface, violating this condition. Violating the previous theory. Okay.
I'm sorry, what is H1 is torsion?
It's okay. B1 is 0 if you want. Yeah. Okay. Yeah. Okay. And actually, I think it's also an interesting question, but of course, not as interesting as the Milnor conjecture, but for instance, it'd be nice to study the rigidity version of these statements. I'm sorry, I need to assume strictly positive here. Okay.
So the Milnor conjecture is that it was proved. What was the Milnor conjecture?
Oh, I mean, it's completely independent of this, right? So Ricci non-negative in any dimension means pi1 finitely generated.
N equals 2 is true.
Yes. Yeah, I think it's an interesting question if you assume everywhere let's say non-negative Ricci 2. Do we have splitting, for instance? This is unknown. Okay, I have let's say a little bit more than 10 minutes. So if you want to hear about the proof, what were some other interesting examples? Maybe examples. Okay. Here's another, I think, quite interesting example. So we mentioned the theorem works for sectional curvature non-negative. It works for Ricci 2 non-negative. Okay, so the question is, can you weaken Ricci 2 to Ricci non-negative? Okay, so question. It's still a question. Let me write. Can we replace the assumption step by Ricci non-negative? So we have the following example, which does not answer the question in the negative, but it kind of suggests that it's a delicate issue. So the example is that there exists, I'm gonna, there exists a four-dimensional closed symplectic boundary geometry, and the two-sided minimal immersion, let's say M3 inside immersed X4G, such that the Ricci curvature, the full Ricci tensor is at least 1 in some delta neighborhood of the image of this immersion. Okay. So so in particular, this implies scalar curvature is strictly bounded below, and since it's closed, so weakly bounded geometry. So, but on the other hand, we can only guarantee this in some tiny neighborhood of the image of the immersion. We're not sure whether this can hold globally in the entire manifold. Okay, but on the other hand, if you just try to play around with the second, the second variation, the stability inequality. Now that stability inequality is purely local. Okay, so this example shows that you can't just prove the same thing with Ricci non-negative by a local analysis. Okay, does that make sense? Okay. All right, so let's look at this example.
I mean, all the methods that are used use local.
That's not true. That's not true.
Yes,
yeah. For instance, let me mention something that's not entirely local. There's this famous, it's a quite interesting paper by Peter Li and Jiaping Wang. They analyzed stable minimal surfaces using Boltzmann functions. For instance, it is known that on a Ricci non-negative manifold, Boltzmann function is always, let's say, sub or superharmonic, right? I think subharmonic. Okay, but to prove that, you need more than just just local analysis on a hypersurface, for instance. You need to take geodesics connecting 2 points, but you don't know that geodesics, it's contained in some neighborhood of the minimal hypersurface. Okay, so they use Boltzmann function restricted on a stable minimal hypersurface to study the minimal hypersurfaces. So this is one example of not entirely local analysis. Okay, so let's see this example. So let me write a sketch. So what we will do is that we take M0 to be S2 cross S1, connect the sum with S2 cross S1. Okay, so then Shen Yao, also Gromov-Lawson, said that, well, on this manifold, there exists a positive scalar curvature metric, right? But in particular, by Custom-Warner, there exists a metric H0 such that scalar curvature is identically 0. You can always decrease scalar curvature, but not increase always. Okay, so let's fix a H0 metric such that on M0, the scalar curvature is identically 0. Okay, so the observation is that now pi1, the fundamental group of this manifold, is equal to, well, S2 well, this manifold deformation contracts to S1 wedge, right? Figure 8. So pi 1 of M0 is the free group of 2 generators. Okay. So this group is not amenable. Whatever it means. Now, a theorem by, so now let's take the universal cover MH to be universal cover. Okay. A beautiful theorem by Brooks. It's a very, very nice paper using minimal surface to study geometric group theory. But the conclusion is that lambda 1, if you take the universal cover of a closed manifold and study its first eigenvalue, just the first eigenvalue of Laplacian operator, okay? So this is 0 if and only if pi 1m is amenable. So in our particular case, we know F2 is not amenable. Therefore, this means that lambda 1 of our MH is strictly positive. Okay. All right. So this is the first observation. So now we're going to do the following construction. So we take epsilon to be this lambda 1 over 6. And we consider, and we take t to be some minus delta, where I'm going to specify delta later. And consider a sequence of metrics ht to be h0 plus t squared times 2 epsilon h0 minus the Ricci curvature of h0. Okay, so you will see why we take such a make such a choice. And then our manifold is going to be the delta neighborhood of this immersion x4 is going to be our m0 cross minus delta delta, where the metric is given by dt squared in this delta direction plus ht. Okay. So it's a trick, for instance, Christens and I used a lot of time. So you just cook up a sequence of metrics in the Fermi normal coordinates, and specifically once we do that, we know the second fundamental form of immersion, for instance, when t equal to 0, is just a minus 1/2 dht over dt. Okay. So you see, the t dependence is a square, right? So this is 0. Okay, meaning that the embedding m0 into this product is totally geodesic. Okay, and moreover, we have the Riccati equation. So the Riccati equation says that a dot, if you take the t derivative and plus a square, then view that symmetric positive definite two tensors. Or if you want, replace a by the shape operator to make everything clear notationally. But anyway, the Riccati equation says that this is the ambient Riemann tensor in the dt direction. Okay. So let's see what it says given this particular choice. So a at 0, so at t equal to 0, we see that a is 0. So the second order derivative, so minus 1/2 t squared ht dt equals to the Riemann tensor on g dt like this. But these, what is that? You take one, so this is precisely minus 2 epsilon h0 plus, let's see, did I already mess up? Okay, let's put a minus sign, okay? I'm sorry. So 2 epsilon h0 minus Ricci h0 equals rg of dot dt dot. Okay, moving the Ricci to the right-hand side, you have that. Okay, but now remember we have a total geodesic embedding, right? So Ricci of h0 it's just if you add one more term in the dt direction, so this tells you that in the tangential directions, Ricci of the G at tangential directions EI, it's just 2 epsilon. Okay, you have all the tangential direction Ricci and one more direction given by dt. Okay, so you have that. Okay. Now, of course, this is positive. Moreover, let's see, we have one more direction. So Ricci, let's see, how do we say that? Yeah, the Ricci of dt, this is equal to, let's see, G. This is equal to the summation over Rg of EI dt EI. So this is according to this equation here, right? So that's minus 2 epsilon repeated 3 times, okay? And subtract Ricci H0 in the EI direction, okay? So this is 6 epsilon minus scalar curvature of H0, which we take to be 0. Okay, so this is 6 epsilon. Okay, so after all these manipulations, the upshot is that Ricci curvature, in ambient Ricci curvature, is always larger than or equal to 2 epsilon on M0 cross 0. So by taking delta, take delta small. So we guarantee Ricci curvatures, let's say, bigger than epsilon. Okay, so this is true in the delta neighborhood of the image. Okay, but now let's take the universal cover M H, which compose with the covering map and the isometric embedding into a M0 cross minus delta delta. Okay, so this is a totally geodesic immersion. All right, such that so we know lambda 1 is, by Brooks theorem, we know lambda 1 is non-negative. So for every compactly supported C1 function, this is bigger than or equal to lambda 1 times the phi square. But remember, we take epsilon to be lambda 1 over 6. Right? So this is larger than or equal to lambda 1, so let's say epsilon times the Ricci nu. Right? Ricci is between 2 epsilon and 6 epsilon, okay, times phi square. Okay, so it's stable. Sorry, time. I think this finishes this example, and I'm sorry I don't have any time to go into proofs, but we can discuss later, I think.